In this session we begin the first and second of 5 examples where we will use the proof by contradiction using the pumping lemma to show that 5 particular languages are not regular. In other words, there's no DFA that recognizes that language. Okay? And you may ask, why 5? That seems a lot. Usually some principle gets illustrated by 2, sometimes 3 examples. Why 5? Well, things get complicated. Now the very first example we will do is fairly easy, and then the second one will be a sort of variant of the first one, but with a complication. And it progressively gets more complicated. So you need, Sipser provides 5 cases to cover these increasingly subtle, relatively more complicated cases as we go through the examples. Right. So hopefully this session will be a bit shorter than the previous two. Right. So in each case we're given a language, right? A set of strings, and each language is described by a property that each string in that language has, right? So here's our first language, and it's of the form, the strings in your language, they're of the form 0 to the power n times 1 to the power n, where n is non-negative. These are integers assumed. Okay, so you'll for a given integer, positive integer, non-negative integer n, you'll have a bunch of zeros followed by the same number, a bunch of ones. So zeros, for example, 0, 0, 0, 1, 1, 1, 1. Okay, the number of zeros, the number of ones will be equal, right? Because you've got the same n here. That's your language. And you're asked to show that this language is non-regular, meaning you cannot have a finite automaton, an FA, a DFA, that recognizes it. Right? In other words, there's no DFA by definition, that has a finite amount of memory, resources, to recognize it. You'd need an infinite amount of memory to recognize such a language. Okay, so we're trying to prove this language B, with strings like this, having this property, that language cannot be recognized by a DFA. In other words, it's non-regular. Right? So we have to prove that B is non-regular. Now, in all 5 of these examples, we use the proof strategy that we discussed in chapter 0, and that proof strategy is proof by contradiction. Right? So, in other words, we're trying to prove B is non-regular. So, if you're going to use a proof by contradiction, you start with the opposite of what you're trying to prove. Right? So, I'll say again, we're trying to prove that B is non-regular. So, the opposite of that would be that it's not true that B is non-regular. Or, in other words, B is not regular. In other words, B is regular. Okay, so we start with the assumption that B is regular. And then we get a contradiction. And we get the contradiction by using the pumping lemma. Okay, so the pumping lemma now becomes a basic tool to obtain the contradiction. Okay? Now once we have the contradiction, then we use modus tollens, the logical inference rule, to deduce that the assumption that B is regular, that assumption must be false. Therefore, B is not regular, or it's a non-regular language. All right. Okay. So we start with the assumption that B is regular. That's the opposite of what we're trying to prove. Right? But we start with that. So we assume B is regular. Now if it's regular, let little p be the pumping length, as given in the pumping lemma, and let's choose, and here's where the art of the proof comes in. Choosing a particular candidate string S that you hope will disobey one of the three conditions, one or more of the three conditions of pumping lemma. Choosing a string that would do that for you may not be easy. It may be quite non-trivial. So here's an assumption being made, right? So we're making a choice of the string. Now let's choose the end here. So we're choosing for the end here. We're choosing the value p, little p, and what's p? Well, it's the pumping length, as in the pumping lemma. Right? So we're letting n be p, and from this assumption we will deduce a contradiction, and therefore we have found a string S, of this form, that disobeys the three conditions, or one of the three conditions, one or more of the three conditions of the pumping lemma, and therefore the pumping lemma has been contradicted. Therefore, this language B cannot be regular. All right. Okay, let's see what we can do with this now. Right. Now, if B is regular, then this string, it's the length of this string, the length of S, will be greater than P. That's sort of obvious, I assume, right? What is the length of this string? Well, 2P, right? You have you have P zeros in your string, followed by P ones in your string. So the length of this string, S, will be P plus P, right? Just 2P. That should be fairly obvious. Well, 2P is greater than P, right? So the length of this string will be greater than P, right? Well, therefore it satisfies a condition using the pumping lemma, that therefore this string here can be split into three substrings, x, y, and z, and that string, x, y, z, or S, can be pumped, right? And therefore x, y to the I, z, that pumped or expanded string also belongs to the language, right? That comes out of the pumping lemma. Well, that's the problem. Okay, so this string here is, its length is larger than P, and therefore the pumping lemma guarantees that this string can be split into three pieces, x, y, z. Okay. Now, so for any non-negative integer I, this pumped string, here it is here, also belongs to B, belongs to the language. Okay? Right? Well, we can consider, now here's an example, it was a bit vague before, but now it's becoming a bit more concrete. Now there are like three cases for this, that we can consider for this pumped string. Now one is the Y, where are we? Here. The Y here, there are only three possible cases. Now Y here, it could consist of all zeros, it could consist of all ones, or it could consist of a mix of zeros and ones. Right? That's all possible cases there are. Right? So let's consider those three categories, three cases individually, one by one. All right. Okay. So if Y consists of all zeros, then this term here with two Y's, now you've pumped it a little bit. So if Y consists of all zeros, then this term here will have more zeros than ones. Now, why is that? Is that obvious? Well, because you've had, now before you pumped it, before you put an extra y in the string, before it was just x, y, z, right? And x, y, z was your s, right? That was one of your strings, and that string belongs to b, and therefore your x, y, z must be of this form, okay? Because it belongs to this language. And therefore your x, y, z has an equal number of zeros and ones, right? Well, now you've pumped it a little and you put in an extra y, and that y consists, in this case 1, consists of all zeros. Therefore, this x, y, y, z must have more zeros in it than ones.